Hey guys, welcome back. Last set of notes here for chapter 45. I really should have just wrapped it up in the last video. I apologize for that. We don't have hardly anything left, just one section, but that's okay because that one section is pretty cool. So this is biogeography. Biogeography is the distribution of species, where they live on the globe, and the patterns, where they live, why they live there, that kind of stuff, and how that plays a role with our community structure. So the number of species globally is going to be its densest close to the equator. And it actually declines as you move towards the poles. There's a variety of reasons for this. One, the equator's pretty much warm more or less all year, and so animals are going to survive a lot better, whereas harsh winters in the far north are going to be a difficult thing. But really, I think it stems from plant diversity. The plants are incredibly biodiverse at the equator, and so there are more pollinators for those plants, more animals that eat those plants, and more predators to eat those animals. And so it starts off with a very, very biodiverse base of the food web and kind of builds up to an even more biodiverse a place overall. Whereas you move to the far north, and there's only a few species of trees that are hardy enough to survive the cold, and a few species of grasses, and your biodiversity is very low at the beginning, and it continues to be very low as you move up. So you get a little more sunlight at that equator. You get a little more rainfall near the equator. Communities have also been established a lot longer, especially if you consider there's reasonable evidence that there might have been glaciers covering a lot of the northern latitudes, and the glaciers receded. Those communities have not had as long to become established as communities near the equator. And the idea that species richness may be self-reinforcing is kind of like what I had mentioned, where the more diverse plants require more diverse pollinators. More diverse pollinators allow for more diverse animals that eat bugs. And so you start with a really good species richness, and that kind of reinforces the entire system to be very species rich. So you can get maps like this for reptiles, amphibians, mammals, all sorts of things. This one happens to be plants, and it's kind of like a weather graph almost, but it's diversity. And so the red and the purple are the most biodiverse, the highest concentrations of different species. And then the pale yellow and pale green are a lower biodiversity or numbers of species. And so you can see that, in the far north, all the way across is, yellow and pale green and dark green. Further south you go, yellow, pale green, yellow, pale green. And really it's along this equator right here that you see these areas first crop up, where there's purple and then there's reds. And so those are the most biodiverse areas. And of course, a lot of these are rainforest areas and jungles where their most biodiverse plant species are found. So another really cool example of community formation is islands. We haven't had the opportunity to watch a lot of new islands be born. So a lot of the work we've done on islands like Hawaii, for example, the island has existed longer than we've known about it, and so we weren't actually able to see it first be colonized. We just show up and we see all these plants and all these birds and all these things that have been there presumably for quite a while. But this did happen in the 1960s. Underwater volcano gradually built its way up. And broke the surface of the ocean. And as it continued to let lava out, the lava cooled in the water and became more land. And so in the 1960s, we were actually able to watch an island come into being. And really, it just started off as black, hot rock. But as that rock cooled, and over the years that followed, bacteria started to get onto the rocks. Fungi started to get onto the rocks just from the ocean. And then lichens followed, and mosses followed, because the lichens and mosses, they really don't need much in the way of soil at all, especially the lichens. But as the lichens and mosses died and were decomposed by that bacteria, they became the foundation for soil. And so new vascular plants were introduced as seagulls started to colonize that island and lay eggs there and live there for short periods of time. Those seagulls would bring seeds in their feces of new vascular plants, and so pretty soon we started to get grasses and more biodiversity on this island. And so it really taught us a lot about how islands originally become populated, how long it takes for an island to become more biodiverse. And we got some pretty cool models built off of observations like this. and we call it the equilibrium model of island biogeography. And that model describes a balance between immigration rates, how quickly are new species coming in, and the species that were there, how quickly are they becoming extinct? Because with succession, the first guys to show up on the scene are later outcompeted by people, and I shouldn't say people, by organisms that they create a good environment for. So as the grasses get there, they're more competitive than the lichens, and the lichens are going to die. And so the island size is a factor of this. This is the island. The island is called Surtsey. This is what Surtsey looked like in the 60s when it was first forming. It's literally just billowing smoke and lava into the ocean. And this is what Surtsey looks like now. There are still some bare kind of dirt areas or rock areas, but you can see here there's some green, there's some biodiversity here, and it's a rather small island. There's not a lot on it. And so here's your really cool patterns with biodiversity. There's a couple of ideas. One is the size of the island. The bigger the island, the more biodiversity it's going to support. Kind of a no-duh thing, right? And so here's the island's distance, or rather area. This is how big the island is. So a very, very small island, you know, it'd be 5 square kilometers. That's barely anything, you know, up to, you know, 50,000 or 500,000 square kilometers. So the bigger the island, the general trend is the more biodiversity it can support. The other thing to bear in mind is how far the island is from the mainland. Islands that are closer to the mainland is the green line, and islands that are further from the mainland is the orange line. And so the idea here is when you start off close to the mainland, you have a much better chance of having surviving animals make the journey to the island. If you're very far from the mainland, you can still become biodiverse, but you start with much fewer species and have to gradually work your way up. Whereas if you're close to the mainland, you're going to start getting more species more quickly because it's closer to the mainland. So that's the end of our chapter. Points to ponder: what characteristics distinguish a pioneer species? Are pioneer species good competitors against later successional species? And why are pioneer species dependent upon the frequent advent of open, disturbed places? So a few questions to kick around. As always, thanks for your time.